Okay. Good morning, everybody. Thank you very much for coming here today. Today, I have the pleasure to introduce you Professor Hugh Christian. He's coming from Alabama. He was the leader of the Atmospheric Electricity Group of NASA Marshall Space Center for almost 25 years. Okay? And he's now a research professor at the University of Alabama at Huntsville. Professor Christian was a principal investigator and pioneer designer of 4 space-based lightning detectors. Okay? The USA is nowadays the only country with this technology. Okay? And he was the PI of the optical transient detector, was in space between 1955 and 2000, the lightning imaging sensor, LIS, on the TRIN satellite from 1998 to 2015, and on the ISS, International Space Station, from 2017 and now, up to now, is working. And finally, he's also the designer and PI of the geostationary lightning mapper, okay, which is the first lightning detector in geostationary orbit. It was launched a couple of years ago, November 2016. Okay, this is a great achievement. Professor Christian is also a world-known expert in high-speed lightning spectroscopy. In fact, that was the reason he came here to work with us for a couple of weeks. He was, in the 80s, he was the pioneer in high-altitude U-2 flights to detect lightning, optical emissions. And I also want to emphasize that he's the author or co-author of many seminal papers on atmospheric electricity, including the first paper reporting global lightning frequency from space and the detections of terrestrial gamma ray flashes produced by thunderstorms in 1994. Professor Christian was the invited speaker of the last edition of the AGU4 meeting in 2017 that was organized in New Orleans, and he was the invited lecturer, as I was saying, of the well-known and very prestigious Benjamin Franklin Lecture to honor the life and work of a scientist in the field of atmospheric and space electricity. So thank you very much for coming, and please take the chair.
Thank you very much. Lovely introduction. The title of my talk is Lightning from Space to Space. I apologize ahead of time. I'm trying to cover too much, and I'm going to skip some of it and try to finish on time at about 12:20. I really should change the name because it's going to be from lightning from space to space, because I'm going to start talking about space-based lightning observations and finish up trying to get into some of the details of the physics of ground-based observations of lightning. So we're going to cover a lot of different territory. Lightning has been studied for centuries, probably most prominently starting with Benjamin Franklin, as Paco said. It's quite complex physics involved, lots of different types of physics, but we're starting to really gain better insights into it using modern technology. And there's lots of outstanding questions still. For instance, how do clouds generate electricity? And by studying lightning, what can it tell us about the cloud? I'll try to discuss some of this. How is lightning started? Once started, how does it keep propagating for tens or even hundreds of kilometers? How are MeV photons generated within a lightning thunderstorm? Why does a lightning leader step? It moves a distance like 50 meters and pauses and moves another 50 meters. Why? And what are the physical characteristics of a lightning channel? So let's start off. This is what you typically see of lightning. This is the time picture, but this is what you see when you look from above. It's just a blob of light, because what you're seeing coming out of the top of the cloud is a lightning channels that are hundreds of optical depths deep within the cloud, and so it goes through thousands of scattering. So all you see now is a blob of light coming out of the top of the cloud. To give you an idea of how a thunderstorm works is that you get typically most air mass storms, you get some heating in the earth. It causes some upward convection. As the air packets rise, they expand, they cool, and the water starts to condense. And water is the fuel of a thunderstorm. All the energy that's produced in a thunderstorm is because of the transition from vapor phase to liquid phase to ice phase. That releases the energy that you see. So as it grows, It goes up above the freezing level, at which point ice starts to form, and you get ice graupel, larger ice particles, and ice crystals, which tend to keep rising in the storm. And it's this interaction of particles that generates charge separation typically between the small ice crystals and the larger graupel, with the ice crystals being left positively charged, the graupel being left negatively charged. And because these are lighter, they get carried up in the updraft, and it causes gravitational separation between the particles. As it continues, you usually get your first lightning flash when the fields are strong enough between the mid-negative charge and the upper positive charge. This continues to expand until you start getting more and more lighting, including some cloud to ground eventually. And as it reaches its peak, you can generate severe weather like tornadoes or hail or straight line winds. But as soon as the thunderstorm starts to collapse, the lightning cease. So the whole lightning process follows the history of the thunderstorm. This is just more of a schematic showing the collision between the larger graupel and the negative ice crystal and the physical separation. And we call this the non-inductive charging mechanism because of the physical collision between the two different kinds of ice particles. And the necessary condition, we think, for thunderstorm electrification is you have to have a strong enough updraft to grow precipitation-sized ice, and you have to have ice graupel collisions in the presence of water, because that seems to be a key in allowing the charge to exchange readily. So, why is remote sensing of lightning valuable? Why do we want to go to space with lightning? There's a number of different reasons. Most of the electrical energy generated in a thunderstorm is dissipated by lightning. So if you observe lightning, you get an idea how much electrical energy is generated. And this flash rate can be quantitatively related, but not perfectly, to electrical energy generation. This was shown many years ago with the ER2 experiment we did, where we measured optical characteristics of lightning. We also measured the vector electric field and the conductivity, which allowed us to calculate, by flying over the top of the storms, calculate what the total current generator of the storm was if we assume symmetry. We could then at the same time measure the lightning flash rates, and we got a result to show that flash rates tend to be linearly, at least for single storms, related to the current. The higher the flash rate, the stronger the charging current of the storm. So by measuring flash rates, which we could do from space, we get an estimate of how much current is being generated. Secondly, the electrical energy is generated during ice production. The amount of lightning is quantitatively related to the amount of ice. This shows you the original ice flux hypothesis that John Latham and I developed many, many years ago, in which we think the relationship, the electrical energy is only generated when ice is being generated and not by static ice. And it's related to the amount of precipitation ice and the amount of ice crystals. And this has been supported by some simple calculations by Alan Blythe, and Marcia Baker did a more complex model back in the 90s to support this work. And then we had a graduate student, Wiebke Derling, who did some work with both lightning measurements and Doppler radar, dual-phase Doppler radars in the Great Plains and in Huntsville, Alabama. And she showed that independent of the location, there was a strong relationship with the amount of precipitable ice mass generated in the thunderstorm and the total lightning flash rates, the two different regimes. Thirdly, electrical energy is active. The generator is active only during the updraft phase, and basically lightning mirrors the thunderstorm development. And this is a case study we did in Huntsville, showing the life history of the total lightning that was measured and the life history of the storms that's seen by dual-phase Doppler radars. And it showed that during the development phase, the strong updraft is shown here, we saw the lightning flash rates increase dramatically. But as soon as the updraft weakened, a lot of ice being produced weakened, the flash rates dropped off rapidly, and it was followed by a very strong wind burst on the ground. So it was severe weather. So we took this, and then we went down to Florida. It was one of the few areas on the ground we could study total lightning. And we did a series of measurements of looking at storms with radar and the total lightning, and we found this relationship. Here you see a sudden increase in lightning flash rates in this storm here, peaking at this point and then dropping off rapidly. And we found that about 10 minutes after the drop-off, a tornado reached the ground, and we had a total lead time of around 20 minutes. We repeated this experiment many different places. This is in over 1,000 cases. And it was determined that the lightning was a very, very good indicator of storms in the process of going severe. So the probability of detection with lightning by itself was over 80% with a very low false alarm rate. This is much better than radars by itself. And we were able to up the lead time from radars in the U.S., showing lead times for tornado warnings of about 14 minutes to about 22 minutes using lightning. So the combination of lightning, looking for an increase in the flash rates, and radar became a very powerful technique that led to the finally ability to U.S. investing in trying to build a sensor in a geostationary orbit. So these are just some of the major points of severe weather. It's the flash rate, increase in flash rates and the jump signature are a very good indicator of a storm that's intensifying strongly. Its lightning flash rate is strongly related to the storm intensity. It basically follows the updraft, so you know the life history by looking at lightning. And the National Weather Service will soon be using this to identify intensifying from weakening storms, identifying storms in the process of going severe, and other type of threats for improved warning systems. So it's a very operationally strong approach. This all was started many years ago, back in the 90s, when we developed the first lightning sensors to have high performance for space with the optical transit detector and the lightning imaging sensor. The beauty of the lightning imaging sensor was on the tropical rainfall measuring mission, where we had a precipitation radar and a microwave radiometer, so we could actually look at the ice characteristics of the cloud at the same time we looked at the lightning. And this is the kind of global distribution maps we were able to develop with the lightning imaging sensor and the OGD together. And this is a more detail showing, this is a 0.1 degree, which is 10 kilometer degree on Earth, showing the distribution of lightning over the many years we had the sensor available to us. And you can animate this, taking all the years of lightning and putting it together into 1 year, and you can really see how you follow the seasons. You can see how in the northern hemisphere summer, you can really see it intensify in the summer, when the summertime as they heat the Earth going further north, and then as you go into the summer. And there's another way of showing this is here, shown here, where we look at the globe and we watch the time of the year, and you can see how the lightning migrates as a function of heating of the Earth by the sun. Quite dramatic. We could also collapse all this data set into one day, and this is in local time, and you can see it's really driven by solar heating in the late afternoon. All the land masses of the Earth heat up, and it's like the Earth having one heartbeat each day through the heating of the sun as it rotates relative to the sun. If you look at it at universal time, you can see how the sun as it comes across the Earth, you can see it heating up, and you can see a wave passing across the Earth through a lightning response to the solar heating. And it just shows in a simple graph the large land mass outside the tropics in the northern hemisphere really drives the total lighting activity with peak in the northern hemisphere, and you can see how the strong peak in daytime, showing almost all the lightning produced is due to air mass thunderstorms. If you look at the rainfall precipitation around the globe, as shown here by the tropical rainfall measuring mission, the picture is much different than it is for the lightning imaging sensor. But if you take the tropical rainfall measurement and divide it into three categories: warm rain process, which you see over the oceans; deep convection, which you see over land; and stratiform region, you can notice that green pretty well shows the same kind of patterns as the lightning production. Because as we said before, this is another confirmation that lightning is produced in storms that have strong convection and produce lots of ice. And in a global study many years ago showed this independent of regime, whether it's over the ocean, land, or in the transition zones. The lightning flash rate is linearly related to the amount of ice being produced. So it's really ice driving lightning, and so lightning should be a fairly good indicator of ice phase precipitation. Now, I mentioned earlier is that we use, for the jump signature, we use lightning to indicate storm intensification, how much electrical energy is being generated. But there's real problems with doing that alone. You probably can't see this eye chart very well, but you can see that over the ocean, the amount of energy, optical energy being generated, the size of the groups, the number of groups, and so forth is dramatically different. What that's telling us is over the ocean, where you have very low flash rate storms, when they do have a flash, it's much more energetic. So a lot more charge is involved. The stronger fields are being involved, and it causes it's a different scenario. So you have to be a little careful about using simple flash counting to really understand how much total energy is being processed in a thunderstorm. We've been able to do some climatology studies with the lightning imaging sensor, and as you notice that if you look at the life history of the instrument, we've seen no change in the amount of flash rays. There's been debates in the literature on whether a warming climate should produce more. Some people say it should produce more lightning. A recent papers come out saying it should produce less lightning. All I can tell you from our studies is that lightning hasn't changed, which means that it's either balanced or the temperature's been pretty constant. Okay, let's show you some pictures about the geostationary lightning mapper. I haven't gone, because of time, and I'm trying to cover many topics, I haven't really talked much about how these instruments work. But the geostationary lightning mapper is almost considered 100 different LISs all in one package. The Flight Model 1 was launched in November of 2016, as Paco said, on GOES 16. It provides full coverage view of North and South America and adjacent oceans. In March of this year, the second GLM was launched, and it's making measurements right now as we speak. And eventually, it'll move to the GOES West position, and it'll give us coverage all the way from the east coast of New Zealand to the west coast of Africa. And this shows you basically the instrument. It's quite a bit different. Europeans are also building a lightning sensor for GEO, which will be launched in a few years. And it has a much different approach. We did a single telescope approach, which was probably a mistake, but that's what we did. It used a very large CCD. We had to, with various size pixels, we changed the size of the pixels so that we get uniform spatial coverage on the Earth, despite the curvature of the Earth. But it's quite a complex instrument. We use a narrowband interference filter here in collimated space. And it's 1 nanometer wide. Then we have some other filters up here, the solar blocking filters. And the combination of the 1 nanometer wide and a 2.8 nanometer wide filter allows us that for solar intrusion, because they shift at different rates, because this sees plus or minus 8 degrees, and this sees plus or minus 4.8 degrees. At about 10 degrees outside the field of view, no light gets transferred through the filters at all. So that means we have minimized solar intrusion. So we're able to really work during eclipse periods. This shows you the characteristics. It works on a single oxygen emission line. It takes 500 images per second, and it has a 7.7 million bits per downlink. Detection efficiency has about 8 kilometers at nadir, 14 kilometers spatial resolution at field of view. It has between 70 and 90% detection efficiency, and we think it's going to be closer to 90 based on our studies so far. And a lot of the processing of the events are done on the ground. This shows the instrument. This shows calibration with a very large integrated sphere. And it shows a picture here of it getting ready to be mounted onto the satellite, and here it is showing on the satellite right next to the advanced baseline imager. And here's the coverage when we have GOES East and GOES West connected. And you can see it has up to about 54 degrees plus or minus, which is a real advantage. We didn't have to go all the way up to Canada like Europeans are having to go way far north, which is a huge challenge because of the curvature of the Earth. And we think we have pretty good detection efficiency overall, the whole field of view. So I thought I'd show you a picture. This is the first light when we turned it on and opened up the shield, the lens cover, and this just shows you the first thing the instrument saw, and you can see immediately we started seeing lightning. You can see the sun coming across the Earth, and everybody in astrophysics, when they have a new telescope, first light is a real important feature to them. This shows you another example of single day. This is running at 1,000 times real time. You see the light coming across. It's kind of interesting here is that you'll see a solar glint come across the field of view as the sun comes across. Here you're starting to see some lightning activity, and I like this. And here's your solar glint as it sees water as it comes across. You can see it spreading out a little bit. And now we're running 1,000 times real time. You can see the cloud motion. This is pictures directly from the instrument itself. You see these clouds developing now, and now they're producing lightning. You can see the light coming out of the top. When you see persistent light, that means that's where the active cell is, where it's flashing like that. That means that's backside stratiform region. Those are lower flash rate areas, but because of the compressed time, they look like they're quite rapid. Just a picture of GLM and the advanced baseline imager. So it's very high resolution cloud image. You can see the overshooting turrets very easily, and you can see the light puddles coming out of the top of the cloud, like I show in one of the first few pictures. I like this one because now this is for the North America solar eclipse, and you can actually see the shadow of the moon coming across the field of view here. Here's the shadow of the moon. Some pictures in the Amazon basin. Watch as the clouds start to develop here in this area. A lot of small air mass storms. Now they're developing and immediately start seeing lightning produced. And another storm in Conus. You see the cloud motions. Again, this is 1,000 times, and you can see lightning being produced in this storm region up here, and even up here far in Canada. So I thought I'd show, this is 1 week of lightning over South America. So you get to really see how it cycles. It's supposed to be 1 week of lightning over. There it goes. You can see the cloud motions continuing on and lightning lasting 24 hours a day, but most intense during the late afternoon. I'm going to show you just a single flash. This is one real time. This is one very large lightning flash, lasts about 1 second in duration. This is real time. Now I'll give you some context for that flash. This is where it occurred. That's Oklahoma. And now this is slowed down to halftime, and we're keeping it persistent. One flash, 1 second, it moved almost 500 kilometers. And the propagation velocity, the leader of this, was about, I'm going to let you see it again, was about 10 to the 5th meters per second as it propagates across all of Oklahoma. There's a lot of interesting physics going on. And it's just, and we can also have information on how bright the cloud is. You can see this is the optical power density of the data, and you can see in some areas it's quite a lot of optical energy being released. And this is a comparison with some of the ground-based systems in the U.S. This is early on the detection of this is called the Earth networks. This is the National Lightning Detection Network. Both these detect both in cloud and cloud to ground. Earth networks saw 3,917 strokes detected. National networks detected 2,912 strokes, blue, and the GLM detected 52,100 events, which is about 15,611 strokes. Significantly more sensitive than ground-based systems. So now we're getting to the base finally. That was space. And we're going to talk a little bit about various ways to detect lightning and how we use that to try to characterize the observations we make from space. So lightning is very energetic. Typical thunderstorm produces around 10 to the 14 joules, which is equivalent to about a 20 kiloton warhead. The lightning energy is about 0.1%. Temperatures can be in excess of 40,000 degrees C. Peak currents where it can get much greater than 100,000 amps. Tens of coulombs are transferred during the lightning flash. The velocity of the return stroke is in excess of 10 to the 8th meters per second, almost half the speed of light. And the wavelengths of emissions go from about 10 to the minus 12 meters to about 10 to the 7th meters, Schumann resonance. So it covers a whole large area of the electromagnetic spectrum. So how is lightning initiated? Two main theories. One is by hydrometeor breakdown, where you have hydrometeors enhance the electric field at the tips, causing initiation of corona. Other people have thought about cosmic rays causing it. This is kind of get on the discredited side. There's just not enough. It takes a very high energy cosmic ray to produce a conductive path through the atmosphere, maybe 10 to the 18. And they're so rare, this really isn't probable. They have problems here too. The problem is all the measurements that have been made of electric fields inside thunderstorms are well below the breakdown level needed to initiate lightning. Typically, an airplane can't measure at all because it goes in corona, so it can't ever see fields strong enough to break down. Balloon probes have shown fields as strong as about 150 kilovolts per meter, which is well below breakdown levels. So the issue is how do you get fields strong enough? Probably the consensus is now it's enhanced fields due to hydrometeors. I think that's not enough. I think there's other effects I'll discuss about in a little while. So once some of the major questions I mentioned, once it starts propagating, how do you keep it going? So we have lots of ways of looking at lightning and trying to understand what's going on in the cloud. This is a schematic showing what people think how a cloud to ground lightning initiates and works. You have a negative charge region in the center of the cloud, a lower positive. This causes a preferred path to come down, but this lower positive is small amount of charge compared to the negative, so it sees the image charge in the Earth because Earth is a good conductor, so it continues to come down, bringing negative charge along the leader channel. Eventually, the leader channel makes contact with ground, and the charge that's been deposited on the leader channel flows into the Earth, and then propagates upward into the mid-negative, and then brings charge down from there. Often that is followed then by it's called a dart leader instead of a step leader, like in this case, and that brings more negative charge down from this region, again causing another return stroke and carrying more charge away from the negative charge region, eventually lowering it. And this is a picture of when you really have a return stroke. And I define a return stroke as when you make a conductive path between two charge regions or a charge region in the Earth, which basically starts at a large potential difference and causes charge to flow from one section to the other. And this is where the energy is being released, is in the return stroke. And it's the light during this return stroke or intercloud stroke that we see from space. This is an example of a positive cloud to ground that's propagating. This is 10,000 images per second video. You can see this is the leaders coming down. You can see that the tip of it is bright, and in behind it is not so bright. And as the leaders come closer and closer to ground, you start seeing all kinds of sharp spark breakdowns. You can see the leader now is getting down to here. Now you can see it here. And there you have your return stroke. It is orders of magnitude brighter than the other. And now this is what's called continuing current. It's continuing to tap charge from the cloud and bring it to the Earth. So it's staying bright for a long time. And it dies. Another case, but I'm going to just show the initiation of this, because you can see the leaders very clearly coming down. You can see many, many leaders, all trying to get to ground, all trying to be the winner. But there can be only one winner, right? Maybe not. You can look down here, you can actually see two branches near the ground. There. So there was 2-1, which is very rare. And this is an accumulation of all the light we saw before the return stroke. You can still get you an idea that huge area has been broke. You see, it's breakdown in a very large area, lots of energy being released. So we wanted to try to address how's the best way to verify the lightning being seen from space. What kind of ground-based system do you need to do that? And we set up two systems in Alabama. One is the North Alabama Lightning Mapping Array, which is a typical lightning mapping array, which you have some in Europe. And of course, I know you have a permanent stage. It basically has a narrow band VHF sensor with sampling rate around 20 megahertz, and it looks at a few megahertz. So it's basically looking at small breakdown processes. The other is the North Alabama Marks Meter Array. We named it after Marks Brook. And this is a wide band. We're upgrading this now from 1 hertz to basically DC to 10 megahertz for the new version. But this is what we used in our initial validation. And with this, you can basically see classic electric field change data at various sites on the ground, see the lightning activity on it. With the NAMA, you basically are good for mapping out the regions of cloud where you had breakdown. So the complementary, and this is basically what data sees. These are electric field sensors. These are the HAMA locations at various sites. And these are HAMA detections. The color dots are the LMA detections. And these are locations from the cloud, from the national networks where lightning came to ground. So let's look at a flash. This shows you the radar picture of it. This is the field change. And we'll just watch it how it goes. That came to ground right here. You can see the step leader coming down. This is mainly intercloud activity. All the color ones are intercloud. With some cloud to ground. And you can see this is the first return stroke right here with second and so forth. We could look at intercloud lightning, which looks a lot different. You can see this processing up here. The initial part of the intercloud light goes from the negative charge region to the upper charge region, and most of the charge starts flowing. The strokes occur after that connection is made. And you can see the Marks Meter Array does a very good job of making locations, especially in the negative charge region, compared to the LMA. But what I really want to get at is how do they compare, the two techniques compare to optical measurements from space. So here is a typical time series of LMA locations. This is from Liz flying over the head, this is when Liz detected optical emissions from the storm. The LMA tells you there's lightning, it doesn't tell you, but doesn't correlate with the Liz. So LMA does not see the proper thing. However, if we want to look at the field change network, on this time you'll see some Liz data being shown here. Every time you see a square there, that's a Liz pixel. So here, you can see that cloud to ground. There was a Liz observation, and so forth. So you can see a very strong correlation between the field changes with the field change network and the optical emissions. Those are strokes. The LMA, though, doesn't really correlate well on a one-to-one basis. Here's another example. You can see, again, it shows you how bright the color shows the brightness of the stroke. There's a misalignment here because of parallax, and the pointing of the trim satellite wasn't quite proper. We can also use the field change network to estimate how much charge has been moved and where the charge came from by measuring the size of the electrostatic component of the field change. And at each of the different sites, we can then do a fitting, not by time of arrival, by amplitude, though. If you have enough sites, you can determine where that charge was located and what its amplitude was. And that's each one of these gray spots is a charge location and amplitude. So that gives you information. Here's another example. In this particular case, you can see here, we said the charge location was centered there, tended to be horizontally spread out, and it had to give an amplitude. With this information, then you can start calculating how much charge was moved, how much energy was involved with the charge movement, and so forth. So it starts giving you an idea of how to address stroke energy. We can also do the same thing with intercloud flashes. Here's an intercloud flash, and you can see the various field change data. And there's the intercloud flash. And so you can look at various changes here in the electric field, and we can then measure that each site, and we can locate where but you have to do it instead of a monopole model, we have to do a dipole model for that. And we can do a dipole model for each step. And here you can see the vertical step was very small, and it was a very small amount of charge transferred, 0.35 coulombs. Here's a larger one, and it was 0.7 coulombs, largest, almost a kilometer distance in that step. And then here you see a very large step. This is the step that connected the negative charge region to the positive charge region and released 8.6 coulombs. So that was where you see a lot of light. And that allows us to actually get at the energy and then be able to compare the ground-based optical energy with the space-based energy. Another way of doing calibration is using the NASA ER2. We did a collaborative work with a series of other people. We wanted to look at TGFs, terrestrial gamma ray flashes, which are basically detected from space. They're flashes of high energy gamma rays up to 40 MeV produced in thunderstorms. So we instrumented an instrument with an array of photometers, a total of 30 photometers, a fast and slow electric field change meter, and then 7 total gamma ray sensors. And that just shows you the field of view of the photometers. This shows you the picture of them. We call the cross-eye fly's eye because the window was smaller, which we had to look at angles. And this shows you most of it's at 77, 74, which our optical sensor in space is, but we have some other wavelengths we also look at, and we also look at wideband. This is just a picture of some of the scintillation detectors. And this is an example of flying over the top of a thunderstorm. We had 80 hours of flight time. We detected with the optical sensor on the FEGs over 8,000 lightning flashes. Which is the optical sensor show like, and this shows the time domain of GLM would see. Compare that with it. And this shows the pictures of the optical and the field change, fast and slow antennas. And this shows the gamma ray, typical gamma ray sensor. Once it gets to altitude, we see a maximum in the cosmic ray background. And over the total flight time, we saw 0 TGFs, which was pretty surprising. They're rare, but we didn't think it'd be anywhere that rare. Out of 8,000 detected lightning flashes within our we were right over the top. We saw an air glow, which is a constant emission of gamma rays, but it's not a TGF, much weaker event. So the question we asked was, and this shows you a close-up of the air glow. It terminated here, and you can see it was terminated by a lightning flash. And paper will be presented at the next international conference on this. But why didn't we see any TGFs? So I had a graduate student whose PhD is dependent on detecting TGFs. I didn't see any, so we changed our direction. And my hypothesis is that energetic storms, which have high flash rates, strong ice flux, and rapid updrafts, result in very strong turbulence and unequal mixing of the generated charge. And I think breakdown occurs in much weaker fields when you have non-uniform charge distributions. So all the models work with uniform charge distributions. But if you have non-uniform charge, maybe you break down where the ambient field is not so strong. And I think that's supported by the optical measurements we made with Liz, when we saw over the ocean where you had very low flash rate storms, you had very energetic flashes. And I think that's the preferred. You need that kind of environment to produce the TGFs. So the type of storms we were flying over were typically high flash rate storms, which is not conductive for TGFs. Anyway, that's shown here. And also, we were flying over the U.S., over Oklahoma, over Alabama, over the coast of Gulf of Mexico, which are higher latitude, which provide lower cloud tops and less length to the relativistic runaway electron avalanche theory, which is basically a linear accelerator where you have large electric fields over a large distance in the storm. Is once you've initiated free electrons, they'll tend to accelerate it. They gain more energy because the field's strong enough. They'll then have a feedback mechanism and produce large, high energy photons, which then electrons, which then bend bremsstrahl and make MeV, tens of MeV photons. So I think these are the conditions that were set up. So we decided to do a little investigation by combining the GLM with Fermi to see if we can get any kind of relationship between when storms produce lightning, TGFs, and which storms don't. So we were able to look at some Fermi data. We have a total of 81 TGFs, of which 24 within the field of view over this period of time. And what we looked at was the relative timing between when the TGF occurrence and the optical emission. And then we wanted to look at the characteristics of the cell that produced the TGF. And because GLM stares continuously, we're able to look for a period of time 30 minutes before and 30 minutes after the TGF, which is something that was never a capability of before. And optical is much better than before the correlations of TGS with ground-based VHF and VLF data. They had very low detection efficiency, sometimes on the order of 5%. GLM has more like 90% detection efficiency, and you can't tell total energy of the stroke with RF, but you can with optical. So there's some real advantages using optical to try to find out the relationship between TGFs and lightning. This just summarizes what we had, and I have a graduate student who's doing this work. And here's what he kind of tended to find. This was all the optical flashes before the TGF. This is at the time of the TGF. These are optical flashes after. And you can see this particular flash was not very optically bright. And you can see here's the time of the TGF, and here's the time it was the GLM integrates over 2 milliseconds. So this is a 2 millisecond interval, and this is the subsequent one. So this is 1 to 2 milliseconds later, and this is 3 milliseconds later. And this is a chart of the ones we had, and we can see it varied. Some seem to occur within the time frame of the integration of the GLM, but most of them occurred 1 to 3 milliseconds or 2 milliseconds after the TGF. And just some more cases. I just want to show you what a typical single integrated 2 millisecond integrated optical emission from a TGF optical pulse. This is a very bright pulse, and you can see each one of these boxes is 8 kilometers by 8 kilometers of light, and you can see from here to here there's 5 boxes, so that's 40 kilometers. So this is actually a big emission, which occurred just after the TGF. And this is the subsequent frame and the subsequent frame. And so, conclusions that SAMR has at this point is that we tend to see TGS associated with lightning storms that produce low to medium frequency, but not high flash rate storms, which supports the hypothesis. The optical emissions suggest that TGS, which usually come just after the TGF, suggests that the TGFs are in the last stage of the lightning leader going up, as we saw how it goes up, and just before it makes contact with the positive charge region and the stroke occurs, we think that's when the TGF is occurring. So he said it suggests the TGF production mechanism is a lightning leader process, which is certainly, the lightning leader is very hot. It's a very strong field at the tip of the leader, and it certainly produces many high energy electrons. But perhaps if this was the case, so I made this comment here, if this was the case, then TGF should be more common, because we see every intercloud flash is initiated by an upward going lightning leader. So I suspect what you have to have is a combination of the upward going leader, which initiates a large flux of high energy electrons, which then which are then exposed in a field environment where you still have strong electric fields between the tip of that leader and the center of the positive charge region, because the initial stroke is just topping the lower portion of the positive charge region. So you can still have kilometers of acceleration in fields that are quite large that then cause the runaway, relativistic runaway breakdown avalanche. So I suspect it's a hybrid cause. And only when you have strong enough ambient fields with high enough cloud tops so that the fields are closer up do you actually get the TGF. And that's an experiment we want to try to pursue sometime in the future. Now I'll get to the stuff that Taka wants to see. High-speed lightning spectroscopy, and I'll just show a little bit of time because I know I'm running out of time. There's lots of things you can do with it. This is what we had. We did it quite a bit different. We didn't have the cameras as fast as Fernando has. We could only go with the main camera 670 frames per 1,000 frames per second. This is typical what you see. One of the things we're doing is that we were doing triggered lightning measurements. So we knew where the lightning exactly was going to be, and so we were able to go slitless. So we had very high throughput, so we have lots of photons to play with. This shows the lower area where the wire was, and the green is the copper. Sometimes we took spectrum up here where it was still vertical, but didn't have copper contamination, but most of the time we took it down near the Earth. The other advantage of this approach is that we can measure the current of the lightning channel. And it shows a sample spectrum from one event. You can see this is in the section of the mostly dominated by ionized emission lines. This is another example spectrum in the longer wavelengths dominated by neutral emission lines. And I'm just going to show you real quickly some evolution of the spectrum. This is 3 microseconds before the return stroke. This is just before that. This is the first spectrum at the peak of the return stroke. And these red lines show areas where we clearly see double ionized nitrogen lines. This is the next image after that, and all the double ionized nitrogen lines are gone. And then we just go the whole sequence. This is 4 microseconds into it, and so forth, and it just decreases very rapidly. This shows the difference between the first frame and the second frame, and you can see here's the doubly ionized lines, and you can see the singly ionized lines grow on the second frame, but the doubly ionized go away, and that's shown here. If you look at the evolution of the constituents, this is the first frame, and only in the first frame do we see doubly ionized nitrogen. Then we start seeing stronger and stronger singly ionized nitrogen, and it has a half-life of about 5 microseconds, and is gone by 10 microseconds, during which time the neutral lines start dominating. This is neutral nitrogen, and this is H alpha. This shows you the time sequence of the current of a lightning flash. The peak stroke here had 15 kiloamps, and these subsequent strokes varied. This shows you how they fall off. The luminosity, though, falls off much differently. You can see it peaks, but falls off more rapidly initially than the current. This shows you the temperature. It also falls off more rapidly. You can see here 5 microseconds, the peak temperature was over 40,000 degrees C. You can see by 5 microseconds, it was down to about 25,000 degrees C, or 20,000. It shows you how the fall off is. Initially, the optical luminosity falls off much more rapidly than the current, but after 10 microseconds, they basically follow each other. So basically, if you can measure the luminosity well, you can get an idea of the amount of current that's flowing in that channel. This shows you temperature versus current, and this shows you the number density profile, which peaks up here almost at just under 10 to the 26 electrons per cubic meter. And notice how it falls off. In 5 microseconds, it's falling off very rapidly, then very slowly. That's the period of time the channel is expanding due to the heat. It's heating, it's very high current flowing, and that's basically, you have a shock wave that's occurring, and the shock wave is expanding, and that's what you hear is thunder. So most of the energy is going into the the hydrodynamic expansion of that channel. Once that channel is finished expanding, then you basically have a very gradual change. And that's why we're seeing the fall off of the temperature very rapidly and the fall off of the luminosity very rapidly, because the energy is not going into heating of the channel as much during those periods of time. You can look at the electron pressure. You can see it's 300 atmospheres in our first measurement, and then falls off very rapidly. And if you look at the number density and current, you can see they match each other very well with time. We can look at I talked about leaders earlier. This is a leader coming down, dark leader. Here's the spectrum from the leader. You can see it's very hot, well over 20,000 degrees C. But look how rapidly, this is the next frame and the next frame. It falls off very rapidly. And that's the bright head. The bright head is probably less than 10 meters long, because the time frame, this leader is probably moving around 10 to the 7th meters per second. And 1.5 microseconds later, it's almost gone. So you can see it's a very small ball of very bright luminosity. Current's flowing into the head of the leader, but there's not much current flowing in behind it. And we have things called continuing current, and every time we see a change in the current, we see a change in the luminosity. They follow each other. Same with temperature, and I think I'll just call that because I think I'm out of time.
Okay, Hugh, thank you very much for a very nice talk. So the paper is questions open. So if anyone wants to ask any questions, please go ahead. Okay.
The summary plot of the amount of the variation of lighting across the year that you showed for the first experiment was here about 27 years summary. That you mentioned you don't see any change with the global warming. You don't see the change on the mean value, but do you see the change in the variance, in the amplitude of the variations?
Yes, no variation, absolutely.
Not even the amplitude of the number of light.
Of the optical emissions?
Yeah.
That plot was just of flash rates, not of the amplitude of the flashes. No, we haven't done that. Is that what you're asking? Let's just go back to it.
The rate that you show.
Let's go back to that. This variation is seasonal.
And the peak-to-peak variation that is
Seasonal, yeah. In the northern hemisphere, summer, much more light than you do in the northern hemisphere winter.
Doesn't change either.
Yeah, this is just basically the average of the peaks, fitting doing a linear fit from here through here, and it's extremely constant. I mean, if you want to do a shorter period of time, you might see some change because you see some big dip here, but overall, it's been very constant. Now, you notice that if you look at the unfiltered events, you see this increase over here. That's due to solar cycle.
Okay.
Because as we go through the South Atlantic anomaly, it compresses, and during the active period of the solar cycle, or inactive period of the solar cycle, we see a lot more collisions to our CCD, and we see events that are not due to lightning, but due to high energy particle collisions. But when you take that out, you filter that out, that pretty well goes away.
Last question for the experiment. Why did you choose a filter in about 700 nanometers rather than white light?
Choose 7774? Yeah. Because it's a number of reasons. It's the strongest light emissions that we see over a period of time. If you look at microseconds, it's not. But we had to integrate over 2 milliseconds. So over a whole pulse, and the pulse we see typically lasts about half a millisecond that we see from space. It gives us our strongest emission. Secondly, it gives us the most consistent emission. Every flash had strong 77, 74 emissions, whereas some flashes had quite a bit of variance in H alpha, for instance, depending how much water there was very variable. 5001 tended to be variable depending on how hot the channel was. But the 77, 74 was always bright based on our U2 measurements, so we selected it.
Oh, hello. Did you talk about why the reason for the anti-correlation with the solar activity?
Yeah. It's a matter of the South Atlantic anomaly. It expands or compresses. And at the altitude our airplane was, the spacecraft was, we got the basically we saw a larger South Atlantic anomaly during that period of time with more electron hits on the CCD.
Galactic rays activity?
We don't see any relationship that we know of with cosmic rays. They're too few compared to the hundreds of hits we get from electrons. When we go through the South Atlantic anomaly, the instrument actually saturates because there's so many hits. It fills up a fight phone. We quit taking data for a period of time. But they're all random, so we're able to look at, and lightning is coherent in time and space. So we're able to actually look for coherency and determine whether it was a lightning event or whether it was a high energy electron event.
So I'm interested about the mechanism of production of gamma rays in TGFs. Mainly, my field is AGN and particular blazars, and I see some similarities with the mechanism which produces gamma rays in blazars, which is mainly inverse quantum emission. Essentially, it's thought to be infrared or optical emission, the one that creates an intense photon field that hits relativistic electrons that then decrease their energy and then scatter the optical photons to produce gamma rays. So, is it known what is the? I guess you know what is the energy levels of the electrons, if they are relativistic or not? If this is a relativistic process in TGFs or not? And is there any claim that this is inverse quantum emission as well, or is it Brensarlum?
Most of the people working in this field, I'm peripheral on it, so it's not my main area. But most people, there's two basic theories for the production of the gamma ray flashes. One is you basically are in an environment where you have strong electric fields and higher altitudes where you have longer mean-free path. So if you get an MEV electron emitted, either by a cosmic ray or by a leader, it then will tend to accelerate in this electric field, and the field's strong enough in the mean heat path is low enough, it will then gain more energy from the electric field than it loses through collisions. So that's what they call the relativistic runaway electron theory. So just basically it keeps getting faster and faster within the volume of the vertical volume of the electric field. If obviously then it gets enough energy, you can then get some pair production, electron positive pair production, which gives you another feedback mechanism because the positrons start going down, they collide, and they basically just accelerates. There's been a lot of Gent4 modeling of this. And basically it works if the electric field is strong enough and long enough, kilometer or whatever, then you basically can account for the amount of the flux of high energy gamma rays. You see it at satellite orbits. There's been a number of satellites that have seen these, including Fermi, including the old Compton planetary, and number of them recently, number of different satellites have seen it. So it's clearly it exists. The other main theory is that it can be done just by the streamer, the leader itself, because the leader itself the tip of the leader is way beyond breakdown. So basically you can easily produce many MEV electrons off the tip of the leader. But I think it's not quite enough. Measurements at the ground have shown with leaders coming down, they see X-rays. They don't see a big enough burst to be what's called a full gamma ray flash. But they see lots of emissions of X-rays. With each step of the leader, you see X-rays. So it's definitely producing high energy electrons, which then bremsstrahl into photons. So the question is, how do you get enough out of the top of the cloud? So the basic theory now is either it's a runaway, it's an avalanche, thinking of the cloud as a linear accelerator of the electrons.
I'd like to come back to the inception of lightning. In your diagrams, you have the negative charge region, and the lower positive charge region. And as a leader descends throughout the lower positive charge region, the positive charge gets annihilated. Is that always the case? Does it translate into breakdown pulses and etc., or can the leader go through the lower positive charge without annihilating it totally, etc.?
I don't know if it annihilates the lower positive. The lower positive is much weaker. The amount of coulombs in the lower positive seems to be a few. The amount of coulombs in the negative charge region could be tens to maybe 100 coulombs. So it's 2 orders of magnitude stronger. We think modeling suggests that in order to get a negative, the preferred path typically, if you had no lower positive, is that you would get only intercloud lightning from the positive, because that's the easier breakdown path. But if the lower positive increases the electric field, the downward gradient of the electric field, so it starts the initiation. But as it progresses down, it sees the image charge of the negative charge region. It gets very intense. I mean, it gets stronger. So I think it just keeps it driving straight through. But whether it's pauses there, I don't know. That's a good question. Whether you see some sort of a pause or extra branching, I think that's a real good question.
Okay. Any more questions?